Good morning, everybody. Time again for quantitative big imaging. And today I'm going to talk about shape analysis. And let's see, doesn't work. Oh, doesn't want it all today. Okay, that's why. No, doesn't want it. Okay. So what we want to, in the end, is quantify something out of our images. And things we want to quantify are, for example, where and how big things are in the image. It's good if you can say something about the shape sometimes. It depends on the questions, of course. We can also compare different sizes, comes back to the question of how big things are. And we can compare different images and see if there are differences between them and what differences where it lies in terms of these objects. And once we have identified the objects, we can also do finite element simulations, we can do image renderings, and for the visualization. So there are a lot of things we can do once we have identified objects. The first step to do it is, of course, to look at the segmentation. So the first is to have segmented images. So looking at the whole chain we have done until now, we have acquisition that produces quite a lot of data, 56 gigabytes in this example. And mostly you need to do some filtering. And during the filtering, you land in the same amount of data. So then you have actually an additional 56 gigabytes of data because you usually keep the raw data a while. Then when you do the segmentation, then all of a sudden you reduce the data a lot, because then you could in principle save the data with 1 bit instead of 32 when you would work with floating point. And that would reduce the whole 56 gigabytes into 1.75 gigabytes. And it's, first of all, more handleable in even a laptop today. 56 gigabytes, then you need quite a powerful workstation to get that amount of memory. That's not the normal stock home computer anymore. And so what we wanted to measure is, for example, volume fractions, counting cells, maybe looking at how the cells are shaped, or any other object for that matter. Can also look into variability within some, say, a cluster of cells or within the volume. So there's a lot of things we want to measure. And the first step to do to be able to measure it is to identify these objects. Metrics that we can talk about are, for example, surface area or volume. No, yeah, surface area is, I was confusing it with the area of the object itself. Surface area or perimeter length, if it's 2D images. We can look at counting, the shape tensor, and principal component analysis, looking at if the objects are some kind of blobs or round ellipsoid representations. So having some, actually making the shape abstract into ellipses and quantify that. Looking at anisotropy or blatedness. That is, if you have these ellipsoids, if they are flat or more ball-like. And then we can also look at mesh and scale-free metrics. On this matter, there is a lot of literature. The first two are probably the more relevant, more important. That's actually large books. Again, coming back to John Ross, gives an overview of different metrics, showing what they can do. Morphometry in R, then you can also get more about the metrics themselves. Then there are specified books on principal components and shape tensors, is more papers. And now to work today. We need a lot of modules, as you can see. And that saves us from writing too much code. There will be some code today showing some algorithms, how they work. So very basic algorithms, how they work. But let's first start just about talking about component labeling. So what we did last week was we segmented the image into being background or the object you want to look at. And that's just a big bucket of pixels, nothing else. It doesn't tell you anything about the image more than you have in total so many pixels that are belonging to the class you want to look at. But now we want to uniquely identify these objects, and that is where the component labeling comes in. A very basic labeling is just looking at separated objects and seeing putting labels on them. So here you have an example. In this image, you have this bi-level image from the segmentation, and then you run it through labeling. And after the labeling, you have 3 different colors here, and each color represents an ID number of that specific item. So it's not the gray level that you measured now, but it's actually an ID number instead. Looking at some real images, this is an example from a big database from street pictures. And here they want to look at where the cars are. And someone already did the segmentation to have some ground truth. You can see, let's see if that one actually works or not. No, maybe I didn't charge it. You can see here, you have some cars. Some are hidden behind signs. Others, as back here, are hidden by, I think there is a man here, and some trees. And that you can see also in the segmentation that you have some cars, they are cut up in several pieces. But anyway, that is what we have as input data for the labeling. And now there are a lot of algorithms. Some are more primitive, good to show the principle. For example, the one I'm going to show you soon. And in scikit image, in the morphology section, there is a function called label. And the labeling can happen with different connectivities. There could be one connectivity, then you just take the horizontal and vertical direction for connecting and looking at which pixels would belong to this object. If you have 2 connectivity, then you actually look at all pixels, so also in the diagonals. This diagonal connection close-up, I actually don't understand, to be honest. But anyway, the 2 main ones are 1 connectivity and 2 connectivity. Sometimes it's also said to be 4 connected and 8 connected neighborhoods. So there are different names on this. This also works in 3D. So if you would have a 3-dimensional image, you can use the same labeling function for that as well. So you don't have to select a separate one. Then the connectivity actually goes in the 3rd dimension too. So then you have 3 typical connectivities. You have a 6 connectivity. That would be the correspondence to 1 connectivity here, but you would have 1 pixel up and 1 down. And the full neighborhood would be 26 connectivity. And then you have actually all pixels around the central pixel. The middle one is something in between, and that would be 18 connectivity. Then you take off all the corners, and then you get some kind of cross-like shape. So if we run the labeling on this image, so it's plain and simple, just taking the command label, bringing in the black and white segmented image. And the output is an image looking like this, where you have different colors. So it's just a color map to show the different image, pieces here. And the thing with color maps when you work with labeled images is that it's sometimes to distinguish if two items have the same label or not. So actually, I think I showed that next week. I will show you a way to produce randomized color maps, which then makes it much easier to see the items. And but anyway, here it's sufficient to use the color map with these colors. You can see that this goes green, orange, and so on. And now we can look at the area of each segment. So what we would do is to count the area of the object is essentially just counting the pixels with that specific label. So we can just take, if you have the image F and several labels, that would be the I here, then you can just count all the position, all the pixels that belong to that item. That you can do using for loop if you like. Then you have to go through each one and of the labels and go through the image every time and count. A more efficient way is to use the histogram, because the histogram actually does the counting for you. So and then the output is then the area in the histogram. Important here is now that you have to set the histogram number of bins equal to the number of labels you have. Otherwise, it doesn't work. What you can see here is we have a logarithmic scale on the y-axis. So we have a lot of pixels on the 0, which is the background. Makes sense. And then we have between 50 and 1,000 pixels for the remaining objects in this image. So the large object would be the orange one here, and then we have down here, we have some few pixel counts on the remaining of this chopped up car behind the trees. And a very basic component labeling algorithm, then to demonstrate the principle, would be that we have this image, we have the black and white. In the case, we have just 4 diagonal lines. And this is our test image that we are going to work with. And the initialization of the labeling algorithm is just that we take each pixel that is foreground gets an index number equal to the running number of the position. So it would be the row plus the column times the width plus 1. That would be the label index for the starting point. And what you can see here now, you have on the first position, you have a 1. And then it goes vertically. And then you see here that you have a 9 at this corner. And then you go up again. And then that would be the next one here, 11, and so on. So then you have, you're going all the way to 81, label 81. Now we want to update this in a way that we can identify or actually cluster together all pixels in this image somehow. And the neighborhood we're going to use is I would prefer to say 8 connected neighborhood. In the way of scikit image, it would be 2 connectivity. And this algorithm is more like it's comparable to the brush fire that just runs out over the landscape and burns off from the starting point. And looking now at each point belonging to the foreground, then we look around its neighborhood. This N here is neighborhood. And if the pixels in the neighborhood belong to the foreground, then you should set the label of that pixel to the minimum label of that neighborhood. So for example, going back here, looking at this one, then you can see, looking at its neighborhood, we have these pixels, and that would mean this pixel here would get the 1 because that's the minimum of this neighborhood. And that would be iteration 1. If you go to this one, then this one would get a 9, and that one would get a 49, and so on. And yeah, then you would get a first clustering in this iteration. And then you have to repeat this several times until no more labels are changed. And the code for doing this looks something like this. It's 4 coupled for loops. 2 is about scanning the whole image, and 2 are for scanning the neighborhood. I'm not going in the very deep detail of this, but you can see here that you have these 2 loops. They are for the image, and if the image is in the foreground, then it does this piece here. And then afterwards, it does some grouping. And afterwards, when you run it, you can see how the pixels and the iterations are running on. So here you can see what the iterations look like. That you get, as I said, the first iteration, you get these 1s here, you get the 49s here, 51s here, and the 9s here. When you run it the next time, then you see that the 1 region and then a 9 region and 49 region, they are growing. And in the end, you have resulted in 4 labeled regions, one with the ID 1, 49, 9, and 51. Sometimes there are other algorithms that would more label the objects more sequential in a sequence. But in the end, what we are looking for is actually just to get an ID number of each object. So this can be animated, making it looking beautiful, and you can see how the algorithm is working. And this is one way of doing the labeling. And as you could see, we needed to do 4 iterations to achieve this. The number of iterations you need to do depends on the complexity and how many pixels you have to label. So there are actually algorithms that can do the labeling in 1 scan from the top to bottom, and 1 scan from bottom to top, and then have the whole labeling done. So that's much more efficient. Other ones, they're working with more region growing. So it's more or less doing a first scan, identifying a region, and then from there, poof, let it grow out into the other regions. Different approaches, and that can be found also in these 2 books here. So if we have a bigger image, so this is one of the cars from the cityscape picture. And we have 2 parts. That is probably a tree or street sign, I don't know. But anyway, there's a line across it. And the binary image only has 1s and 0s. And now when we start doing the initial labels, you can see here that we have a lot of labels. So each pixel now has got its own label. And we want to run this. Then we do the same code essentially. And it does a couple of iterations. You can see in this case, we needed actually to do 8 iterations instead. In the beginning, there were many groups, and then it reduces into 2 groups. And after that, it stabilizes and doesn't do much more. And animating this, you can see how the labeling is working. going from the top to down, and you can see how it's growing out and relabeling actually all the pixels into 2 blocks. Now, what happens if we don't use a 3x3 neighborhood? We maybe want to use a larger neighborhood, speed up things, for example. That would be at the cost of a coarser labeling. So let's see what this does. In this case, in the previous example, we had the neighborhood scan going from -1 to +1. Now instead we do a -2 to +2 scanning. That's the only change of the algorithm now. And looking at what happens then, is with this large block, you can see that the whole item is actually labeled as the same. So you have 2 pieces, but they're labeled as the same. And the reason is that you can see if we have a 2x2 and 5x5 neighborhood and put it around this point, for example, then you have +-2 that would actually reach to this point and reach this point. Yeah, that point. And that means we will label both objects into one. You do the labeling in less iterations, but you may do a bit too much reduction of the objects. Maybe that is what you want, depends on your application. Another option is going for a smaller kernel. Yes? Yeah. Yeah. I would probably go rather for doing the closing. But yeah, I would think I would go for the closing. It feels more logical. I mean, it's better to have the items as they should be before you start doing more analysis than trying to do some analysis and during the analysis bunch it together. I think to me it makes more sense to do it with the closing. The closing, of course, can, well, the larger neighborhood can also have the same problem, that it's actually putting together too many pieces. But that is some balance you have to explore and see. Where do you get the best performance? The other one option is to have a smaller kernel. In this case, we only have the neighbors up and down and sideways. And if we run that, then we have a little bit more complicated things here to check if the radius is less or equal to 1. But otherwise, again, that's the modification. And nah, that wasn't meant to happen. And if you look at this, it's first, if you compare to the previous to the first one with the 3x3 neighborhood, now you can see it's actually getting a diagonal front in the labeling. That gives you a little bit more detail, but you may also lose, for example, items that are. So, for example, you can see here that you get 3 objects. This red item is a new object because the 4x4, the 4 neighborhood can't actually reach it. So that is another way of doing it. The reason to go for that kind of neighborhood is mostly speed, because you have to check 4 less neighbors, which in that case also means, first of all, the comparison operations, but also the memory access. So that can gain you some time if you need to speed up things, but it can cost you some accuracy in the labeling. So if we look at what we achieve with the different neighborhoods. We have the 3x3 closed in 9 iterations. You got 2 segments, which made sense. The 5x5 finished quicker, but in less iterations. But on the other hand, you only got 2 segments. And then with a cross, you iterate a lot, and you got 3 segments. And which one you choose depends on what makes sense on your applications. In some cases, it's maybe better to do the cross than the 3x3. 5x5, I don't think usually algorithms have implemented, so you have to implement it yourself, I think. I haven't seen it, at least. And so what can we now measure now that we have these objects labeled? As I already said, the area or volume is just counting the voxels or pixels. And then we can also look at change in surface area when you do some kind of erosion and dilation. In principle, to get the surface area, the easiest way is just to erode and subtract the eroded from the original, and then you get the pixels on the perimeter. And that would be a way to get the surface area. There are more advanced ones, but I'm not going to show them here. And what we want to do is, for example, counting cells, tell something about the cells, and then maybe compare between different batches. But how can we do this now? One thing is to look at positions. So looking at the center of volume or center of area. And that's in principle an average of the positions in X and Y. And let's see, was this code? Actually, I didn't, that was not so important to show. We have this labeled image. We have now I use again the scikit image labeling, and we see we get 2 objects, 1 and 2, and from those we want to do some kind of estimation of the position. And the center is more or less the average of the pixel positions for each direction. So first you take the average of x's belonging to, so for example here, you take x position from this one, this one, this one, this one, and so on, and take the average of the x positions that you have found for that object. Then you do the same thing for the y direction. Then you take all the y positions in this object. And finally, and that will give us some kind of position. And looking at the extraction, you can see here, I have extracted the x coordinates, the y coordinates, and then in the end, I compute the averages for the x column and y column. And that gives me the average position in x and y around here, which makes sense. And this is the way you compute the center of volume or area. A modified version of it is looking at center of mass. Then we don't only look at the shape of the object, but also at the gray distribution, gray level distribution in the image. And again, you look at now the position and weighted by the gray level. There is a difference between them, and that I'm going to show you. Let's see, that one is ready. So here we have an image. It had some kind of gray level gradient in it. The segmented image is just a black and white, showing where the box is. And then we want to compare the two. So we compute, again, we extract where we have the positions. And from these arrays with the positions, we compute the average for just the coordinates. And then we compute the averages of the coordinates times the value divided by the value average. And that gives us actually two different positions. The red dot gives us a center of volume, which is in the middle of the square. And now that you can see we have a heavier weight on the lower right corner, we can see that the blue dot, which is center of mass, is moving towards that one. Which one you're using depends again on what you want to know. Mostly when I use position measurements, I use the center of volume. But sometimes it could make sense. Actually, I can't give an example right now, but it could make sense to also use the center of mass. And yeah, we want to know a lot of metrics about these objects, as many as possible to begin with, to see which one makes sense. And implementing all this, you know how to compute the area. I showed you how to compute the position of the object, but we can also look at perimeter length, how to do that, sphericity, orientation, if you have not round object, but a little bit stretched out object, orientation do they have, and so on. And there is a nice function in scikit-image called region props, and it gives us all these and a lot of more metrics. So looking at the help of this one, you can see that there is a very long list of different properties that you can measure. And I'm actually not going to explain all of these because they're, as you can see, quite many. So once you want to investigate different properties, it's probably better to look at the manual and see which one would fit your purpose. So there are, to group them, there are area type of metrics, there are shape related metrics, there are position related metrics, yeah, and so on. Let's see. Yeah, and then there are also higher statistical moments to be measured. And if we now have done the segmentation on an image, I think it's still the car image, then we can look at all the regions. So we just call this region properties, where we have the segmented image and we have the intensity image, which is a gray image. Then we go through all the different properties and look at what it gives us. And you can see here, it gives us a quite long list of different metrics. Computing each metric costs you time. So there is also a possibility to say, I only want these. So you can reduce it into less objects. Some interesting ones is, for example, here, a bounding box, which I'm going to show you soon. It's more or less just draws a frame, the box that includes the whole item. So, of course, it's a lot of information you get. Everything is very technical, abstract, very specific, but it's not really related maybe to the questions you want to ask and the things you want to know. And you maybe want to know something else than how long is a cell in the x direction. Doesn't really make sense. The cell could be rotated and have different sizes in the x direction. So that doesn't really make sense. So instead, you need to know something else. And we could look at different orientation, the length along different axes instead. That would make more sense. And here you can see, let's see here. Yeah, in each direction. So let's look at this car and see what we can measure about it and tell about it. First, we want to find a bounding box. It gives us that the pixel x goes from, in the x direction, it goes from 4 to 12. So you can see here, it goes, as said, from 4 till 12. Looks more like 15, but, sorry, I'm confusing rows and columns again. So from 4 till 12, that makes sense. And in y, it goes from 3 till 15. So this is what the bounding box gives us. And we can draw the box. So that would be something like this. The thing about using these is often very useful. For one, to just show the area you want to tell something about. For example, if you do a region selection for computing some statistics, it's usually good when you present the results to show these boxes around. It's just visualization, but it helps you to explain this was the area and this is something I'm telling something about. So this would get, you would get from the patch collection. So you have here rectangles, and then you can tell a lot of how to set it up. And you can also add this to the figure afterwards. So now let's look at the street view again. And we have the cars there. And let's look at the shapes of these cars. The first thing is we can identify the center. We can get some boxes around them. Over here, you get many boxes because the trees and so on. What you can also look at is statistics around these different metrics. And we can even, based on the analysis, we can add some actually, what's it called? Literal labeling on the colors based on what the combination in them. And then we do this analysis using a k-neighbors classifier to get the class names. And afterwards, we can get here the bounding box. It has some area, some centroid, and we can even assign a color to these objects. And it tells us that it's dim gray, silver, dark slate gray, probably more or less all gray, it seems. And then there's one that's called powder blue. Which one was that? That was, yeah, okay. I wouldn't call that powder blue, but okay. It was misclassification, I would say. So another thing is, I already said objects are not always round, even though in physics, people like to model things as balls, but in real world, things are elongated. They are not as one convex shape. But one thing to look at is anastrophe, if you have more or less convex objects. And in principle, what anastrophe is, that is the object varies differently in different directions. And it could be tall and skinny, if you describe people, tall and skinny, short and fat, or maybe perfectly round. That's not a nice description of a person. Now is the question, how can we describe these vague descriptions? Instead, we want to have some metrics on it, and one would be longest side divided by shortest side minus 1, could be 1. way of describing it. At my shortest side over longest side, and so on. You can have many combinations how to describe it, and which one you use is, I would again say, something you have to ask yourself if what purpose. So that is to explore what you need and what makes physically sense in your investigation. So here is some little code where I define all these metrics that I showed on the previous slide. And it's done as so-called Lambda functions. It's a little trick that is used in Python. And here you can see how this shape is changing and how the different anisotropy metrics behave. And some of them increases all the time and other ones not so much. So there is always an increase in anisotropy in each metric, but some of them behave very differently. And with that, you really have to explore what kind of behavior you want to look for, what shape. So I can imagine these will be more dedicated for certain issues of minor and major axis. And they're more sensitive in this range. And going for statistical tools, we have a lot of stuff. There's a lot of courses on linear algebra, statistic courses, and so on. And all that is a bunch of math. Maybe it doesn't really look like something you can use always, but some of these tools can actually be used in real world with images too. I will also give, in 2 weeks, there is more about statistics, but let's look at one tool that comes very handy, and that's principal component analysis, which is a kind of wrapping up the images to be statistically independent. So what you're doing is to compute the covariance matrix of your signals. Let's see, yeah. And then you do an eigenvalue decomposition. So now we have combined both statistics and linear algebra and bring them together. And the matrix that results, the eigenvector matrix, can be used to transform your data to being independent vectors. May sound abstract, and looking at an example, here we have, this is just a toy example, so these are fabricated data, but should resemble some kind of IR spectrum. In one case, we only have noise. In another case, we have some fat spectrum, and the last one is a protein spectrum. And you can see the difference lies mainly in that in this case, you have 2 peaks, and in this case, you have a 3rd peak also in the spectrum. And looking at some measurements on this, it's not always easy to decide, is this measurement really protein or is it really fat? And in particular, not when we have a lot of measurements, and try to look at these together with noise. And if we want to compare different data, one way would just be to plot all these points in the same plot, just a mess. We could also compare 2 signals against each other. As you can see, if we do a scatter plot of 2 curves, it doesn't really make sense at all. You can't see anything that makes sense. Now, let's run this through the principal component analysis. In this case, I'm running it on 5 components. And the result is that now that we have transformed it using this orthogonalization, all of a sudden, the scatter plot very clearly identifies you have 3 different classes, and these classes can easily be segmented in a later case. So with this transformation, you really made sense out of data that didn't make any sense at all. Now let's go on with this. And then you can see how important is each component. And you can see that from the eigenvalues of this decomposition, you can see that the first 2, they make a lot of sense. They have a lot of energy in them, while the other 3 doesn't make much sense. So that also gives us an idea how to use these eigenvectors for the transformation. Yes. This is the effect of the principal component 1 and 2. So I had this transformation, and for the so I first did the decomposition. I get the eigenvector matrix, which I use only 2 of the transform vectors to get this information. Yeah, they are not really X and Y values. They are linear combinations of the signals, and these linear combinations, they are orthogonal to each other. This one. Yeah, here I took 2 curves, two measured curves, and tried to plot them against each other. Yeah, so I take plots. So the data point of curve 1 and data point of curve 2, and plot them together. So that's probably land here, and then I take next point, and so on. So I just take 2 signals like this and plotted them as a pair. That gives this scatter plot. So I think it's break time. So let's make a break.